10.1.2. On this half of the lesson, we're going to talk about significance tests for P1 and P2. So, an observed difference between two sample proportions can reflect an actual difference in the parameters, or it may just be by chance at the variation of the random samplings or the random assignment, as in you could have just accidentally just chose a bad sample, or it could be a real difference between those two populations. Significance tests can help us decide which makes more sense. So here's our null hypothesis. The null hypothesis says that the population in 1 subtract population in 2 equals our hypothesized value. It's what we think it actually is. We'll restrict ourselves to the observation in which the hypothesized value is 0. This is the null hypothesis says that there's no difference between the parameters. So this means that if P1 take away P2 equals 0, or you could also say that P1 and P2 are the same, as in there's no difference in the effect of maybe the drug on a person's cholesterol level. The alternative hypothesis says what kind of difference we actually expect, as in is one actually is better than the other. Here's our example from our textbook. It's talking about hungry children. Take a minute to read this example, and we're going to talk about how to actually solve it next. Researchers designed a survey to compare the proportion of children who come to school without eating breakfast in a low-income elementary school. A simple random sample of 80 students from school 1 found that 19 had not eaten breakfast. At school 2, a simple random sample of 150 found that 26 had not eaten breakfast. More than 1,500 students attend the school. Do these data give convincing evidence of a difference in the population proportions? All right, so our state appropriate hypotheses for the significance test to answer the question and define the parameter of use. So basically, we want to know if there's a difference in population. So basically, we could say H null is that the populations are the same. Population 1 equals population 2. Or we could say that population 1 take away population 2 equals 0. And the alternative hypothesis would be that the difference in population 1 and population 2 is not equal to 0. We're not trying to prove is one greater than the other or one less than the other. We're just trying to prove that they're not the same. So that's why we have the not equal to symbol. And we're going to state what P1 is. P1 is the proportion of students at school 1 who did not eat breakfast, and P2 is the true portion of students at school 2 who did not eat breakfast. So our first step is going to be to state our null and alternative hypothesis. The conditions for performing a significance test about P1 take away P2 are the same as constructing a confidence interval. So all those things we've been learning for a while, we've been doing for a while is it random? Is it a 10% of the population? And do we have large counts, as in does N ticket times P greater than 10? N1 times P1 greater than or equal to 10? And is N1 times the complement greater than or equal to 10? Same thing with N2. Is N2 times P1, P2 greater than or equal to 10? And N2 times its complement also greater than or equal to 10. At some point, we're going to find a z-score for that value, and then we're going to find a probability of finding that z-score. So we're going to answer the question. So basically, the z-score is essentially p hat sub 1 take away p hat sub 2 take away 0. So this is our statistic. What we think about the population. So this is our population part statistic. This is our what we think the mean for our parameter is. We think the difference in those parameters, P take away P1, we think that difference is 0. It's going to be divided by the standard deviation of the statistic. We have a new symbol here, P hat C. Basically, it means combined probability. So basically, that's all the pool sample proportion. It's basically the count of all successes for both samples combined divided by the count of all individual samples combined. So basically, the formula for it is P hat sub C is the first sample plus the second sample, all the ones that are collected, divided by all the people who are actually in each of those surveys. So again, simply, this P hat sub C represents the overall proportion of successes of the combined samples, basically combining both of those. And you'll see what I mean in this example in just a moment. So our alternative says that if that difference is greater than 0, we look on the high end. If the difference is less than 0, we look on the left tail. If that difference is not equal to 0, we're going to double one of those tails to get that combined probability. All right, whenever we begin these tests, we have having the difference in these proportions. Y'all can start with a state. You're going to actually go to the plan, and then you're going to go to do. And after you do, you're going to conclude. This is your checklist. So when you answer these, and if it's a short answer, you want to make sure you have this checklist written out. Did you state your hypothesis and your alternative hypothesis? All right, we already did this part already. And this is the same example that we began with. Did you make a plan? So in this case, the plan is if conditions are met, we should perform a 2-sample z-test for P1 take away P2. So we're going to check if the conditions are met. Is it random? Well, the data is performed using 2 independent random samples, 80 students from one school and 150 from another. So it was random, so we can check that part off. Did the 10% rule apply? The researchers are sampling without replacement. So we can check the 10% conditions. There are at least 10 times 80 or 800 students at school 1 and 10 times 1500, 10 times 450 equals 1500 students at school 2. The sample without replacement tells us that it's independent because I know it's an independent sample, and also it's less than 10% of the population. So we're good to go on the 10% rule, and we know this data is independent. So we can go on from there. Large counts. So we're going to check the number of the successes and failures. We want to make sure there are at least 10. So in the problem, we had 19 students out of 80 that actually had not eaten breakfast. So we got 19 students out of 80. So my success is here. Success is 19. And then my failures is going to be the difference of that. It's going to be its complement. So it's going to be 80, take away 19. Yeah, that's about 61. Both of those numbers are bigger than 10, so my success and failures for the first set actually works. In my second set, there were 26 students out of a total of 150 students. So my success is 26, and my failures was 150, take away 26, which is definitely bigger than 10. It's going to be actually like 134, no, 124. So my failures is bigger than 10, my success is bigger than 10. So we have our large count rule applying, and that part's good to go. So we did our state, we made our plan. Now we're actually going to do it. So the do is, we're going to find N1 is 80, P hat of 1 is 19 out of 80, or about 23.75%. N2 is 150, so P hat 2 is 26 out of 150, given this value. Our point estimate is the difference between the proportions of P hat 1 take away P hat 2. So P hat 1 is this value, P hat 2 is this value. I got those differences. So my point estimate is here. So in my normal curve, I would have a value right there in the middle of that, it's about 0.0642. I can think about that point estimate this way, or just the middle of a confidence interval. So I'm going to put ends on the interval. And the middle of that interval is 0.0642. And we'll figure out our margin of error to find other ends, because that's what we're making right now, confidence interval. All right, so given that value, it says the pool proportion of students who did not eat breakfast is all the ones who ate the first time, who didn't eat the first time, plus all the ones who did eat the second time, plus all students in the first set and all students in the second sample combined to be this, and that condition is 0.1957. So that is P hat sub C. So we're going to do a two-way table. If we look at this for confirmation, if you look at all this, 45 out of 230, so she'll give you that value. Now let's actually go to our test, our z-score. Our z-score is going to be our statistic, this value, take away our expected difference, 0, divided by the standard deviation of each one of those combined, square rooted. And you'll find this value. So the p-value of all of this, the z-score here is 1.17. So given that information, that z-score is 1.17. And basically, z-score tells you all of this information, right? But you don't really want that information. You're looking at a two-tailed test. What you really want is what's above 1.17 and what's below 1.17. So basically I can find what's above 1.17 and then just double it. So I'm going to go to a z-score table. I'm going to find the area that's above 1.17. So go to my z-score table. You can see this is 1.1. I'm going over to the number 7. That looks to be right here, 0.879. 0.879. So that means this area here is 0.879. So to find the area on the upper end is going to be, this area is going to be 1 take away 0.879, which is about, use the calculator real quick, 0.121. So this area is 0.121, and this area is 0.121. So I can say twice 0.121, which is about 0.242. So that tells us that this is definitely bigger than an alpha level of 0.05. Like that's about 24%. So that means it's not atypical. This is not unusual. So this is our do part. All the stuff we just did here is the do section. Once we get down to this area, I need the curve for both of those. And the last thing I'm going to conclude. So given these z-scores and the area beneath them, we're going to conclude. We conclude that because our p-value is 0.2427 is greater than the alpha level of 0.05, we fail to reject the hypothesis, our null hypothesis. There is not convincing evidence that the true proportion of the students at the school who didn't eat breakfast is different. All right, and those are the steps to doing what we just did. Now, truth be told, a lot of students have errors when doing all these calculations. And it's not expected you actually do all these calculations on the actual AP exam. That's where it comes from, and that's how you understand it. And they may ask you questions about how to derive different parts of it or how to find different parts of it. But you're kind of expected to do this because there's so many parts to it to actually do it with the calculator. So I'm going to show you how to do it with the calculator now. So you go to calculator. Well, you're going to turn the calculator on. And you can go to stat, then go to calculate, stat, go over to test. And then what you want is a 2 proportion z-test. So go down and look for a 2 proportion z-test. And here it is. And in the first sample, I think it was 19 students out of 80. In the second sample, there was 26 students out of 150. And we want to prove that they're not equal to each other. They're not the same, so we can calculate it. And basically, we did the math for it. They said that the z-value is a little bit more accurate than ours. So it got to be 1.68. But they found a p-hat value. P-hats are 1 to be about this. P-hat 1 is this. But they found that probability to be about the same. We said it's about 2.2. 2.2. Anyway, we said our value was about 2.2. 2.42. And they have it here about 2.37. I'm sorry, 2.426. That's pretty close to what we had using the formula for it. Anyway, so we're going to do it this way on the test. And anytime we see a problem like this on our do section, we're going to write down, we're doing a 2 proportion z-test. And we're going to show the value you typed in, and then you can give the output if you want to. And that's how you're going to answer that question on the test. All right, so skipping ahead. Oh, wait a minute. Before I skip ahead, let's go back to drawing it too. So you can draw the picture as well. So we went back to stat. I went over to test and 2 proportion z-test. Instead of calculating it, I could draw a picture of what it should look like. If you go over to draw, it should give you a picture of what that sample is. So it gives you both tails, and it tells you the p-value, and it tells you the z-score that relates to that p-value. So the area between both of those tails is 0.24. And we can prove that that's bigger than 0.05 pretty quickly. Then it says, whether or not we should fail to reject the null or reject the null. All right, be sure to read these 3 paragraphs in your page before you continue the video. So pause the video and read those 3 paragraphs now on inference and for experiments. All right, now that you read it, let's go to the question about cholesterol and heart attacks we began this week with. So right now, reread this example we talked about, and this time you want a alpha level of 0.01, and you want to be really, really accurate. You want an 89% confidence level because we're talking about people dying. So you want to be as accurate as possible because it's a pretty serious thing. And use your calculator to answer this question. But be sure to state what you're going to do. You're going to state, make your plan. You're going to do the do section, and that's going to use the calculator for. And then you're going to write your conclusion. Whether you fail to reject the null or reject the null and put it back into layman's terms of the words of the problem. All right. And after you finish that, we'll talk about that in class. And then you have to check your understanding. So after you finish that, our first example in class would be to check your understanding. That's all I have. Good luck.